Hello and welcome back to your Chem 4 lecture. We are into lecture 3 now. This is going to finish up chapter 2. And today what we're going to talk about is metric units, metric unit prefixes, and then some of the units of measurement that we're going to use throughout the course of the semester, including things like distance, so the meter and its prefix units, as well as volume. And we're going to talk about mass as well, what mass means basically. And then we'll wrap it up with a look at density as well, which is a combination of two of the things that we're going to talk about. But let's go ahead, let's get started just by looking at the metric units themselves. And one of the very special features of metric units that you may be aware of from before, which is that metric units can be modified by a prefix. And this prefix can make the unit either smaller or larger. So for example, we know that meter measures distance, right? And 1 meter is a pretty convenient measurement or unit, I should say, to use when you're measuring someone's height, for example. Like most people are between 1 and 2 meters tall. So that's a convenient unit. It's easy to use. However, that's not as useful if you're trying to say like, how far is it from here to Phoenix, or if you want to drive to San Francisco. That is a very small unit, the meter is, for such a large distance. So what we can do is, rather than use the meter, we can use the kilometer. So the kilo is the prefix here. And what kilo means is just literally 1,000. So 1 kilometer is 1,000 meters. Think of it like this, basically. This is the way I always think of it. It's 1 kilometer is 1,000 meters. And that way you'll always know that 1 km is going to equal 1,000 m. On the other hand, let's say that we're trying to measure, let's just say that we're trying to measure something like, the length of your finger, let's say. Now, a meter is not very useful for that because it's such a tiny distance, right? So you can't really measure it in terms of meters. So you need a much smaller unit in that case. Well, metric prefixes have that covered too. One example would be the prefix milli, and milli means 1/1000th. So 1 millimeter is 1/1000th of a meter, or you could put it this way: it's 0.001 meter. So we use these prefixes again because they're just ways that we can modify our units so that we have just an easy way to compare numbers from one measurement to another, whether we're measuring, again, our height, or let's say that we're trying to measure the length of a cell, for example. A cell is very, very small. So we need a very, very small unit to be able to do that. But ultimately, it's the same quantity, right? It's a length still, if you want to think about it in more abstract terms. So we have the same base unit, but then we modify that base unit so that it's useful on a large scale, on a macro scale, and then on the micro scale as well. Okay, so this is the way you want to think about these prefixes, is that these prefixes will give us a equality that we can use. And remember, an equality, if you recall from your math classes, is just an equation where you have two sides that are equal to one another. So this equality is 1 kilometer equals 1,000 meters. It's very important that we note, 1 kilometer is the exact same as 1,000 meters. That's the definition of 1 kilometer. And so this equality is going to let us do something very useful in the future when we turn this into a conversion factor. And this is the same thing for liters and grams, which we've talked about briefly already. 1 kiloliter would be 1,000 liters. 1 kilogram would be 1,000 grams. And that's always going to be the case. So we want to make sure that we can write these equalities for each of these prefixes. Okay, so here are the prefixes that you have to memorize. We have 2 slides on this, so just keep this in mind. And we'll go through them kind of step by step, but I just want to point out now that these prefixes, again, you'll have to memorize them and what they mean, as well as their abbreviation or the symbol, I guess is what I have it as here. So that you'll be able to do that on the test. Now, this is not going to be the last time we have to memorize something in this class. So what I recommend doing right off the bat is get a set of index cards that you can use to make flashcards. Now, if you don't have access to index cards, ask me in lab, and we'll come up with something for you. Whether that's we can like cut up printer paper in lab. I think we have the cutters there that we can use, and you can just have the pieces of paper where you can kind of look at both sides, or we'll find something in lab for you. Also, there's all these quizzes online. I'll see if I can find one or maybe make one for you, where you have like a Quizlet, I think they're called, where you just like you have a flashcard basically that's on the internet. But okay, we'll work on that. And again, if you need anything, if you need any resources, just go ahead and ask me in lab, and I'll make sure that you get those. Okay, let's look at the prefixes that we're going to need to know. So first up, we have tera. So we're going to start with the big ones, and we're going to start from the highest level that we need to know. Now, there's a bunch of other ones that do exist, but you're not expected to memorize all of the ones. Again, only the ones that I'm highlighting for you here are the ones that matter, or the ones that you have to memorize, I should say. Okay, so tera has the symbol capital T. So like a terameter, for example, would be abbreviated capital T, lowercase m. And the value is basically 10 to the 12th. So that's 1 trillion. Okay, so that's 1 trillion. So you can usually help yourself remember it just by trillion from T, right? Because it's thousand, million, billion, trillion. Okay, yes, just making sure. In scientific notation, that's 10 to the 12th. And again, this is a very big number. So like we wouldn't use this except when we're trying to communicate something that's like for example, very long distance. So like if we're talking about cosmic distances, so distances from one star to another, you could use a terameter, for example. Yeah, and then this is the example here that 1 terasecond would be 1 trillion seconds. So again, that's an enormous amount of time. But since second is the SI unit for time, or the metric unit for time, we wouldn't talk about it in terms of days, even if we're talking about something that takes years and years. We would still have to use seconds and describe it in terms of seconds. So that's why a unit like terasecond might be useful. It's if a process takes a long time. Okay. Oh, you'll also recognize these maybe if you ever have to buy like computer memory, for example. Like recently, hard drives have made it to like the terabyte level. So you may buy a terabyte of memory, and that gives you an idea. It's roughly the same idea. It's like 1 trillion bytes of information. And I don't know a lot about that stuff, but it's the same word. So if you've heard tera before in terms of terabytes, that's referring to this same prefix. Giga, of course, you probably also know like gigabytes from your flash drives, for example. Giga means 1 trillion, which would be 10, I said it wrong, 1 billion, excuse me. Giga, symbol capital G, the numerical value is 1 billion, which is represented in scientific notation as 10 to the 9th. So 1 gigameter, for example, is 1 billion meters. So for example, like the distance from one star to another, you could use that in terms of gigameters, or probably you'd use terameters at that point. But that means that 1 gigameter would be 1 billion meters, or 1 times 10 to the 9th meters. Mega, so mega comes up every so often. It means 1 million. So the symbol here is capital M now. So mega, capital M, kind of get the idea that these larger ones are all capitalized until we get to kilo, which is the next one. So mega means 1 million. So a megameter would be 1 million meters, or a megagram, as what I have here, is 1 million grams. In scientific notation, of course, 1 million is 10 to the 6th. So those are equivalent as well. So 1 megagram is 10 to the 6th grams. Okay, kilo. Now, kilo we've already talked about, right? That's first off, it's abbreviated as lowercase k with a symbol. It means 1,000, so or 10 to the 3rd in scientific notation. And 1 kilometer is 1,000 meters, or 10 to the 3rd meters. Okay, so those are the ones that are important, that are bigger, as far as like making the unit bigger. Now we're going to get to the ones that are going to decrease the size of the unit. And these are ones that you're actually going to run into a lot more in medical practice. So like as you, I think you're going to run into everything from deci, centi, milli, and micro. Potentially nano or pico, maybe not, maybe not, kind of depending on what medicine you're working with. Some drugs are effective in the nano region or nano concentrations, but it's pretty unlikely. Most of the time, we're going to talk about, for example, microliters, milliliters, centiliters, and then deciliters, for example. Okay, I'm getting a little ahead of myself. Apologies, but these are very important. So definitely make sure that you're understanding these that decrease the size of the unit. So now we were taking a unit and making it bigger. Now we're using it and just making it a little bit smaller. So we start with deci, deci like decimal, right? And a decimal is 1/10. So deci means 1/10 or 0.1 of a unit. So 1 deciliter is 0.1 liters. So just you take 10% of whatever it was, that's what the deciliter, that's what that means. And that gives us two separate equalities here. We have 1 deciliter is 10 to the negative 1 liters. So following along again, 0.1 is 10 to the negative 1. And then what that means is 1 liter is made out of 10 deciliters. If you add up 10 deciliters together, that gives you 1 liter of a substance. Centi you're probably familiar with in terms of centimeter, because a centimeter, you may recall, there's 100 centimeters in 1 meter. Well, centi is a prefix that means 0.01 or 1/100th of an object or of a unit that we're talking about. Now that translates to 10 to the negative 2 in terms of scientific notation. So we have that 1 centimeter is 10 to the negative 2 meters, or it's 0.01 meters. And then that also means that if you take 1 meter, that's made of 100 centimeters. Okay, so hopefully this is making sense so far. Next up, we have milli, which is, again, more famous in milliliter. You have probably heard of milliliters before. And milli means 1/1000. So it's 0.001, right? So the 1 is in the thousandths digit. In scientific notation terms, that's 10 to the negative 3. So you could say 1 millisecond is 10 to the negative 3 seconds. Again, we're just making the unit smaller and smaller and smaller. And yeah, milliseconds become important if, like, for example, you're timing something that's very sensitive. So like if you're timing like a track and field event, for example, a track event in particular, then you might measure the time it takes to run in terms of milliseconds. Okay, micro. Now, so micro here has this symbol. So, oh, I guess I mentioned here, milli has the lowercase m as its symbol. Micro has this symbol here, which is mu. Now, in your when you're typing this out in the future, just kind of note it sort of looks like a U, and then on the left side there's a line that goes down. So when you write it in your notebook, for example, or in lab, you can write it out just like this. It's almost like sort of like an M where you collapse it, and then instead of having two humps, there's one sort of valley in the middle. Give it a shot. Why don't you like take a moment here and just write it out. In fact, let me get my pen set up here, and we'll go ahead and work on that together, because this is going to be something that is important. All right, we're back. So again, mu looks like this. It's a Greek letter, and you draw it kind of like that. That was a pretty bad one. Let me go one more time so that you can kind of see it. So you go up, down, up, and then a little bit shorter on the other side. Now, as I recalled this here, I should have referred back to this earlier. The reason I put this slide in here is that when you actually use micro in a medical field, you're going to use MC rather than mu, just because this mu looks a little confusing. And also, if you have to type it out, not all word processors have easy access to this symbol. So I will be accepting MC this semester as the symbol for micro. So just so you know, 1 microgram then is 1/1 millionth of a gram. And again, this comes up a lot in the medical field because many times drugs are effective in the microgram per milliliter range. And so you're going to have concentrations of drugs that are micrograms of the drug for every milliliter volume of the solution. So yeah, so that's going to come up every so often. So that's just kind of giving you this here. Now, again, in chemistry, we use this mu symbol here. So you're going to see it kind of both ways here. All right, so getting smaller now, of course, we had 1/1,000,000th here for micro, which is 10 to the negative 6. Then after that, we have nano. So nano goes another power, 3 powers of 10 to the 1/1,000,000,000th one, which is 10 to the negative 9. Now, once we talk about things like nanometers, for example, 1 nanometer is 10 to the negative 9 meters. Now we're talking on the distance of like molecules. So very, very, very small. Like we're getting down to the very fundamental distances that make up all matter, basically all compounds. And lower than that even is pico. Pico, which is p, lowercase p, of course, nano, lowercase n, pico, lowercase p, is 1/1 trillionth, or 10 to the negative 12. So 1 picosecond would be 1 times 10 to the negative 12 second. The fastest chemical reactions that occur in the universe occur on the order of picoseconds. So we're talking about things like electrons transferring from one atom to another. That's as fast as it gets, and those go on the order of picoseconds. So, yeah, so those are all things. And again, what I'm going to recommend that you do is you make a series of flashcards. And it's up to you how you do it, but I would say the best thing to do is have the symbol and the multiplier in terms of scientific notation, because those are the two that are going to be the most helpful. Now, you need to do whatever you need to do to help you learn it. So if you also want to include the names of it here, so like deci and d, that's totally fine. Most of the symbols are pretty straightforward. Micro probably is the hardest one. Now you can just remember micro can't be M because milli is M. That can help out a lot. But what's the other tricky one? Basically, kilo being lowercase k is kind of tricky, I suppose. Yeah, so make sure that you get those and the multipliers related to each other. Okay, so now just to prove how useful all of this is, just look at the back of like any food that has like the nutritional info on it. And you'll see just a wide variety of units used on that little box that we're so familiar with. So like, for example, you might need 1 gram of calcium. Well, that's because you need quite a bit of calcium to keep your bones, nice and strong. Copper, though, copper is very rarely used in our system, in our bodies, I should say. You don't need much of it. In fact, you only need 2 milligrams per day. Iodine, now iodine is very important that you have it in a certain amount, but it's also very dangerous. It can be poisonous if you have too much iodine. So you only need 150 micrograms of iodine. I think this is per day, yeah, daily values here, compared to 2 milligrams and 1.0 grams. So you need a bunch of calcium, a small amount of copper, and then a very, very small amount of iodine. And that goes on. You see iron, magnesium, niacin, phosphorus all require milligram amounts. Potassium, which is really important for your, it's basically a very important electrolyte. You need 3.5 grams of that. Selenium, again, a nutrient that we only need just a little bit of. That's micrograms amount. And sodium and zinc, sodium needs a gram amount because that's, again, an important electrolyte. And zinc, you just need a tiny bit of zinc, and that is about 15 milligrams there. So you can look at this, for example, your recommended daily amounts. Look at the back of your cereal box when you take a look when you're eating your cereal, and you'll see all these different units listed depending on what you need. Okay, so sample exercise number 13. This isn't really too much of a challenge. Like, obviously, you can look back and make sure that you fill it in. But the idea is here, we want to get the correct prefix for each of these units. So like for A, we have 1,000 meters is equal to 1 blank meters. So what's the correct prefix that should go in there? Do the same thing with B and C. And when we come back, we'll have the answer. The PDF, again, is posted down below this lecture. So go ahead, pause the video, answer the questions, and we'll come back with the answers. Pause. And we're back. So 1,000 meters, hopefully you recognize that was the kilometer. 10 to the negative 6 grams matches the 1/1,000,000th or micro prefix, which would be 1 microgram. And then finally, 0.1 liter, 1/10 of a liter is a deci. So 0.1 liter equals 1 DL, deciliter. Okay, so next up. Now that we understand these prefixes, we're going to focus on the uses for the equalities that come from those prefixes. And we're going to start by talking about length, measuring length. So remember, this equality is going to give us the relationship between the two units that measure the same quantity. So in other words, they're both measuring length. What's the relationship between the two units? Well, 1 meter is 100 centimeters, or 10 squared centimeters. 1 meter is also 1,000 millimeters, and that would be 10 to the third millimeters. Then you could also do an equation where you have 1 centimeter. Well, 1 centimeter equals 10 millimeters. The way that you can actually figure this out is, guess what? We have 1 meter equals 100 centimeters. We have 1 meter equals 1,000 millimeters. Think of it this way. This is A and this is B. This is A and this is C. If A is equal to B and A is equal to C, we know that B has to equal C. In other words, 100 centimeters equals 1,000 millimeters. If you divide both sides of the equation by 100, you get the answer that 1 centimeter equals 10 millimeters. And you can use this with any set of units that you need to. But that's the idea. That's the work. That's how we got to this equation. Okay. Yeah, so again, we basically said that 1 meter is 10 decimeters, which is 100 centimeters, which is 1,000 millimeters. So it's like each of these is kind of the same way of saying, basically, we take this more of the smaller units and they add up to the bigger unit. So 1 meter is composed of 10 decimeters. It's also made of 100 centimeters, and it's also made of 1,000 millimeters. I hope that makes sense. Just the idea is here, this is a meter stick, okay? And the decimeters are measured every 10 centimeters. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimeters in the 1 meter stick. You go one step farther and say, okay, there's 100 centimeters. But you get the idea. There's 100 centimeters here on this ruler. And then if you go farther, you can see, oh, it's 1,000 millimeters is equal to 1 meter. Let me know if that doesn't make sense. I'm happy to help try to explain it. And we'll be in lab as well to work together on this, where you'll see, you'll look at a meter stick and hopefully that'll kind of start to make sense. Similar to like if you've used a yardstick in the past, 1 yard is 36 inches or 1 yard is 3 feet. But it's the same idea. Okay, so that's length. And so, yeah, one of your activities, in the future, if you're working in pediatrics, for example, well, you might have to measure babies. It's never as easy as this one here shows it. It seems pretty well behaved, but okay. So another thing that you'll have to measure and keep track of a lot is volume. So volume, as we talked about, it's just the space that an object occupies. And you're going to use a lot of different volume units throughout your career in health sciences. So if you have a liter volume, so a liter volume, again, I showed you this last time, but this Nalgene bottle here is a 1 liter bottle. That fits 1 liter of a liquid. Now you're going to find it divided, so you can divide it into 10 portions and have a deciliter. You can have it into 1,000 portions and you get a milliliter. So you may need to measure, for example, like the amount of blood that you're giving to a patient. If you need to track the amount of urine that a patient is giving out, you'll be measuring these in terms of milliliters, centiliters, or deciliters, depending on what the instrument that you have measures. Okay, so now here's another thing that's a little different for health sciences in particular, which is the cubic centimeter. So like if you've watched dramas, like medical dramas, for example, on TV, you know that there's always like this, there's a patient coming into the hospital and there's a doctor or someone who's in charge, could be a nurse, could be a doctor, who says, I need 100 cc's of this stat of whatever drug stat. I need 100 cc's of blood. Well, so that cc unit, I think they're getting away from it now. So maybe this isn't going to apply to you at all. That cc unit is what's called a cubic centimeter. So 1 centimeter cubed. Now, this centimeter cubed unit, even though it's a centimeter, this is actually a unit measurement of volume. And the way that it's a unit measurement of volume is 1 cubic centimeter is the volume that's contained in a cube whose side lengths measure 1 centimeter. So if you have a cube here, let me do my best here. Not bad, right? Okay, so here's our cube. This one has a height of 1 centimeter, a length of 1 centimeter, and a width of 1 centimeter. So 1 centimeter times 1 centimeter times 1 centimeter right? Because to get the volume of cube, it's just the length of the cube cubed. So 1 centimeter times 1 centimeter times 1 centimeter, that's 1 centimeter cubed. Now here is the beautiful, beautiful thing about metric units. And this is one of the things that like just makes metric units so wonderful to work with. It's not the only one of these, but this is the most useful one. 1 centimeter cubed, that volume is equal to 1 milliliter. So 1 centimeter cubed is 1 milliliter, which is 1/1000th of a liter. So there, right away with the metric units, we can convert from the length units into the volume units with no friction whatsoever. And then also that is also sometimes put as cc. Again, I think this is old, and I believe they're trying to get away from this. But you may hear it, I don't know, like, you know, maybe you're going to work with older trainers or something like that who will use it. So it's best that you know what cc means now. Yeah, so that's pretty cool. Oh, and as a result of this, if you have a 10 centimeter by 10 centimeter by 10 centimeter cube, so that's so 10 centimeters cubed, that would be 1000 centimeters cubed, and we know that that is equal to 1000 milliliters, which we know equals 1 liter. Whoa, that's pretty cool. So again, we can convert from like a dimensions of length in terms of centimeters directly into a volume unit like liters. Okay, all right. Yeah, again, so the idea here is that the cubic centimeter has the same volume as a milliliter, and you can just interchangeably use those units. So like a syringe, if you need to give 2 cc's to a patient stat, well, okay, so you can just use your syringe, draw out 2 milliliters, make sure there's no air in the needle like they do, it's very dramatic. And you squirt out a little, and it's like, ah. But the 2 milliliters, 2 cc's, that will deliver the same amount. And again, I think they are getting away from cc's. So it's more likely you're going to see centimeters cubed or milliliters. Okay, all right. Again, if you have any questions, ask down below. Yeah, I'll try, again, I'm going to try to like make things as relevant to your future profession as possible. And this is one of the things that you really need to know. So that's why we're spending so much time on it. Okay, next up, mass. Okay, now mass is a little interesting, right? We talked about mass in the previous lecture, and we talked about how basically mass is like the amount of stuff that's in an object. And in metric terms, we use the kilogram. Now, the kilogram is useful because it gives you an idea of your body. Like most people are, you know, between 100 or sorry, they're between like 50 and 150 kilograms, let's say. So that's a pretty convenient way to like compare people's mass or weight. Um, so yeah, so we're going to record the mass in terms of kilograms. Now, if you're administering drugs, drugs are often useful like in the microgram level. So you only need to measure out or mass out, a microgram sample of a certain drug for it to be useful. So again, the idea here is that, bigger things can be measured with the bigger units, smaller things can be measured with the smaller units. And that's what's so convenient about these prefixes. Okay, so here's your different equalities that may come in handy. As we have 1 kilogram equals 1,000 grams, we know that. We know that 1 gram is 1,000 milligrams, right? Because 1 milligram is 1/1000th of a gram. 1 gram is also 100 centigrams. And then if you take 1 milligram is actually 1,000 micrograms. Remember, 1 microgram is 1/1,000,000th of a gram. 1 milligram is 1/1000th. So the relationship there is just of times 1,000. Okay, all right, so here we go. Sample exercise number 14, pretty simple. All you have to do is identify the larger unit for each of these examples. Give it a shot. So A, you have mm or cm. I'm not gonna say it. This is how we're gonna get familiar with these units. And again, the idea is we want the larger unit for each of these. B is kilogram versus centigram. C is dl or μl. And then finally, D is mg or μg. So which one is larger? Go ahead, pause the video. When you come back, you will have the answer. Okay, let's take a look here. So we have millimeter versus centimeter. Which one is bigger? Well, a millimeter is 1/1000th of a meter. A centimeter is 1/100th of a meter. 1/100th is bigger than 1/1000th, so centimeter is bigger. Kilogram versus centigram. No question here, right? A kilogram is 1,000 grams. A centigram is 1/100th of a gram. So a kilogram is way bigger. Okay, deciliter versus microliter. Deciliter is 1/10th of a liter. A microliter is 1/1,000,000th. So the 10th of a liter is definitely bigger. Finally, for D, milligram versus microgram. Well, milligram is 1/1000th of a gram. Microgram is 1/1,000,000th of a gram. 1,000th, again, is much larger than 1/1,000,000th. So we choose milligram in this case. Okay, one more very quick sample exercise before we move on. That's sample exercise 15 here. Complete each of the following equalities. So 1 kilogram, what does it equal? 0.01 centiliters, what does that equal? So give that a shot and go ahead, pause the video now, work this out, and then when we come back, we will have the correct answers on the screen for you. So pause. Okay, now I realized here in just this last moment here that there was a problem with B. We have a problem with B. This should be 1 centiliter here, not 0.01 centiliters. We haven't done that yet, so don't worry. There we go. 1 centiliter is equal to what? So go ahead, give that another shot. You already saw the answer here. It's here. 1 kilogram, of course, 1,000 grams, no problem. 1 centiliter, that means 0.01 liter, because centi means 1/100th. So it's 0.01 of a liter. Okay, so now those are the type of metric equalities that we have kind of defined from the past. But that's not the only kind of equality that's going to be useful to us, especially living in the United States. A lot of times we're going to have imperial or US measurements that then need to be converted into metric measurements in order for them to be useful for a number of different reasons. So we've already seen equalities, how they work between units of the metric system. It could be between US units as well. So like 1 pound equals 16 ounces. You may be familiar with that. And then finally, you can have equalities between metric and US units. For example, 2.20 pounds equals 1 kilogram. So these are all ways that we can kind of understand the relationship between units, whether they're related in the metric system or not. Okay, Now, on food labels, we actually noticed that food labels sometimes have to be marked both in US units and in metric units. So for example, here, this is like a spray. And I think this is some kind of canned peas here. You'll notice the mass, the weight is listed as 1 pound, 12 ounces. And then it's listed additionally as 794 grams for the mass. And again, this is just showing two different systems for measurement here. And it's useful sometimes because sometimes you need, if you have a recipe from not the US, perhaps it measures in terms of grams rather than in terms of pounds. So it can be very useful. A lot of packaging in the United States will have both of them here because a lot of this packaging is also going to be sold, for example, in Canada or Mexico potentially, and you legally have to have the mass in grams for both of those countries. Okay, so now here's a really important thing to note, that significant figures is going to play a big role in our understanding of equalities. So if you're converting from a metric unit to another metric unit, that is by definition just an exact measurement. So 1 gram is exactly 1,000 milligrams. That's an exact number. It's not a measurement, so you don't have to worry about significant figures. However, when you convert, okay, well, sorry, so let's finish that up, because there's 2 US units. When you're converting from US units, again, that's also a definition, so it's an exact number, so infinite significant figures. So like 1 foot equals 12 inches. That's not going to affect our significant figures for any measurement that we're going to make in feet or inches. Same thing with minutes and seconds. Of course, 1 minute is defined as exactly 60 seconds. It's not a measurement. So that's an exact conversion. Now, this is going to make sense when we talk about the other side, which is when we convert from US to a metric unit or vice versa. These now are measurements, okay? So 1 pound is measured as 454 grams. Now, this all of a sudden is going to matter for our significant figures. So 454 grams for 1 pound, that's a 3 significant figure conversion. 946 milliliters for 1 quart, that's a 3 significant figure conversion. 39.4 inches for every 1 meter, 3 significant figure conversion. Okay, so anytime that you're converting from a metric unit to a US unit, or more likely, vice versa, you're going from a US unit to a metric unit, the conversion factor is going to affect your significant figure count when we actually do the math behind it, with one very important exception, and that is this one right, 1 inch equals 2.54 centimeters. In the evolution of the US units, 1 inch is now defined as 2.54 centimeters, so this is an exact conversion. In other words, it's not a measurement. We have designed the inch to be 2.54 centimeters. So by definition, when you're converting from centimeters to inches or inches to centimeters, you use that conversion. That's not going to affect the significant figures in your calculation. Okay, now let's actually show you an example of what that means, because otherwise, it doesn't really make any sense here. So, all right, so let's go ahead and look at conversion factors, because this is what you're actually going to use these equalities to produce. When you have an equality, you can list it as a conversion factor. Okay, so I'll give you the math behind it real quick if you're interested. If you're not interested, don't worry about this part. But if you have an equality, A equals B, okay, well, you can set up a fraction A over B. Now, what does this fraction equal? Well, think about it this way. A is equal to B. So if you were to substitute A for B, you would get A over A. And what is a number divided by itself? That's always going to be equal to 1. So A divided by B is always going to be equal to 1. This is the idea of a conversion factor. Now, the reason that this is going to be useful to us, this might sound stupid. And again, if you don't care about the math part of it, don't worry about it. We're going to show how to use these here in a minute. The reason that this is important is because you can take any number and multiply it by 1, and you're going to end up with the same number. So when we want to convert from one unit to another unit, we want to make sure that we have the same quantity that we start with as what we end with. So this is why a conversion factor that's equal to 1 is so useful. Conversion factor allows us to convert from one unit to another while keeping the same quantity that we have. This is going to make a lot of sense because you do this in your head all the time, right? Like if I say, okay, we need an hour and a half. Well, okay, we're gonna break and we're gonna come back in an hour and a half. Well, you know that an hour and a half is 1.5 hours, and that there's 60 hours in or 60 minutes in 1 hour. So if you take 60 minutes per hour and you multiply, so take 1.5 hours and then multiply it, you have 60 minutes per 1 hour. Well, so, okay, hours are going to cancel out. 1.5 times 60 just equals 90 minutes. So real quick in your head, you did all of this conversion factor stuff without even thinking about it. So now we're just kind of giving you a formal way of showing this conversion factor stuff. And we'll be working on this a lot in lab too. So yeah, so here's the idea. Now, if we have a conversion, if we have an equality that tells us 1 hour equals 60 minutes, there's two different conversion factors that we can get from there. First off, we have 60 minutes divided by 1 hour, or we have 1 hour divided by 60 minutes. Both of these are equivalent. They're both equal to 1, like what we said up here. But they're used in different ways. We can use minutes per hour to convert from hours to minutes, like what we did here. We can use hours per minute to convert from a number of minutes to a number of hours. And again, you can say it this way, it's 60 minutes per 1 hour. Per just means divided by. Okay, and so here's our common equalities. Now, I am going to provide you with all the ones that are necessary on your exam. So now the metric ones you need to memorize, right? Okay, so these are all going to be, memorized based on the prefixes. So memorized from prefix. However, the US and the metric US, all that are needed will be provided on the test. So you'll basically have like an extra sheet on the back of your test that has like a staple, it's stapled to the back of your test, but you can rip it out. And it will have all of the conversion factors that you need. Now, that said, it may not have all of the ones that you want. So like, for example, I may give you 1 yard equals 3 feet, 1 mile equals 5,280 feet, but I may not give you that 1 mile equals that many yards. So you may need to do multiple conversion factors. It also might be that you want to memorize these, and it might be helpful to you to complete the test more quickly. But ultimately, I find that these conversion factors will be provided to you when you need them to do your calculations, so that you just have the you kind of have the opportunity to use the ones that are on the test, because otherwise you don't know which ones to memorize, and it can get a little messy. But again, the metric units now here, this is all this prefix stuff. You need to know all those prefixes, because I'm not going to give those to you on the test. Yeah. Oh, this is something that's useful in, I guess it's useful in medicine, but also in cooking. 5 milliliters is 1 teaspoon, and 15 milliliters is 1 tablespoon. That's very useful. It may come up sometime. Okay, anyways, when we're writing conversion factors, let's say that we have 1 meter equals 100 centimeters. The conversion factors that we would write is that we would say there's 100 centimeters per 1 meter, or there's 1 meter per 100 centimeters. Same deal with metric US system conversion factors, where 1 kilogram equals 2.20 pounds. That means there's 2.20 pounds per 1 kilogram, or 1 kilogram per 2.20 pounds, depending on, again, what conversion you're actually doing. Okay, so why don't you go ahead and give it a shot with sample exercise 16. Write first the equality that we've talked about, and then write the 2 conversion factors that you're going to need for each of the units. So A is liters to milliliters, B is inches in meters, and then finally milligrams and micrograms for C. So go ahead, give it a shot now, pause the video, When you come back, we will have the answers for you. So go ahead, pause. And we're back. So the solution for sample exercise number 16 looks like that. First off, 1 liter equals 1,000 milliliters. So we know that there's 1,000 milliliters per 1 liter, or 1 liter per 1,000 milliliters. Now, I just want to point out here that you may also write the conversion factor as 1 milliliter equals 0.001 liter, because you know that 1 milliliter is 1/1000th of a liter. In that case, your two conversion factors would be 1 milliliter divided by 10 to the -3 liters. And the other one would be 10 to the -3 liters for every 1 milliliter. Okay, 39.4 inches equals 1 meter is for B. So the two conversion factors that you get are 39.4 inches per 1 meter and 1 meter per 39.4 inches. Finally, milligrams and micrograms. So you may recall the way that we did this before is that 1,000 milligrams equals 1 gram. And you also had 1 million micrograms equals 1 gram. Set those equal together. That's 1,000 milligrams equals 1 million micrograms. Divide it out, and it ends up being 1,000 micrograms for every 1 milligram, or 1 milligram for every 1,000 micrograms. Okay, now that's conversion factors in general. But of course, that's not where they end. They're actually extremely important for the types of problems that we're going to solve from now until end of the semester, or at least through the general chemistry, organic chemistry part of the semester. So this is a very important thing to understand. So we're going to build up these problems is by using conversion factors. Okay, so first up, we want to notice conversion factors that occur within a problem. So like, for example, you may have a conversion factor given to you in a problem like this. The car travels at 85 kilometers per hour. Well, the equality is that the car is going to travel a distance of 85 kilometers for every 1 hour that it's traveled. So the conversion factors would be 85 kilometers per hour, like we say, or 1 hour per 85 kilometers. Note here, of course, these are not exact numbers. The 85 kilometer has to be measured. Now the 1 hour is assumed to be exact because you're counting you're not measuring this 1 hour, you're measuring the 85 kilometer distance here. So just keep in mind that also goes back here, 39.4 inches per 1 meter. This 1 meter is exact. The 39.4 though, on the other hand, these have 3 significant figures in them. Oops, okay. All right, so that's the idea, is that's how you can identify a conversion factor that occurs within a problem. Okay, let's do something medical. Well, let's say that you're prescribing a tablet, or you're giving a tablet to a patient. The tablet contains 500 milligrams of vitamin C. That means that the equality that we could write would be 1 tablet equals 500 milligrams of vitamin C. Or in terms of conversion factors, there's 500 milligrams of vitamin C per 1 tablet, and 1 tablet per 500 milligrams. Now, just like what we saw before, the 1 tablet, that's an exact number. However, the 500 milligrams, that's a measurement. A pharmacist or someone measures the amount of vitamin C that goes into the tablet. So a measurement of 500, how many significant figures are there? It's on the slide, but you get the idea. We have a 5, and then 2 trailing zeros and a number without a decimal. That means there should be 1 significant figure. Okay. So those are conversion factors that we might see within a problem that we'll need to use to solve a problem. Okay, another type of conversion factor that you're going to see a lot is a percent. And we'll talk more about percents in a future chapter. But for now, we'll just introduce them and we'll show a way that you can easily get a conversion factor from a given percent. Basically, a percent is going to be written as a conversion factor because you have the unit that expresses the numerical relationship in terms of the parts of the unit per 100 parts of the whole. So if you say that a person has 18% body fat by mass, that means that they have 18 grams or kilograms of body mass for every 100 grams or kilograms of body mass. Now, it's given to you in the equality in terms of kilograms. So in other words, there's 18 kilograms for every 100 kilograms of body mass. Thinking in terms of like, let's say that we have alcohol sanitizer, that's 75% alcohol, and that's by volume. In that case, we would have 75 milliliters of the alcohol for every 100 milliliters of the solution. Similar idea here. This is just in terms of mass. So 18 kilograms body fat equals 100 kilograms of body mass. And 100 kilograms of body mass equals 18 kilograms of body fat. In this case, again, the 18 is what's measured. So there's two significant figures. The 100 kilogram figure is given. It's an exact number. Okay, now here's the type of problem that I'm definitely going to put on the test for you, which is a dosage problem. So there can be equalities that are stated within dosage problems for medications, and these can be written as conversion factors. So Keflex is an antibiotic that's used for respiratory and ear infections, and it's available in a 250 milligram capsule. So one capsule, the equality would be that one capsule equals 250 milligrams of Keflex. In conversion factor terms, that means that there's 250 milligrams of Keflex per one capsule, or one capsule per 250 milligrams of Keflex. Again, the 250 milligrams is what's measured, but one capsule is going to be exact. Remember, that's counted, right? You count one capsule. So in this case, the conversion factor will have two significant figures. And you can imagine why that would be so important. You want to make sure that you give the patient the correct number of capsules of Keflex. Okay, so why don't you go ahead and do that? Give me the equality and the two conversion factors for each of these following problems. We have meters and decimeters. Then we have jewelry that contains 18% gold, and we'll say that's by mass. And then finally, 1 gallon of gas costs $2.40. Okay, let's make this more like today. Let's go ahead and increase this. Let's go ahead and go $5.40. That sounds a little more likely. I remember when gas was $2.40, but it's been a while since I've seen that. So, okay, let's give it a shot. Give me the conversion factors for each of these. Pause the video, work on that, and when you come back, you'll have the answers. So grab pause. And we're back. So we've got meters and decimeters. We know that there's 1 meter per 10 decimeters, or just like what we did before, you could say that there's 0.1 meters for every 1 decimeter. I honestly prefer doing it this way. This way makes more easy sense to me, but if you prefer doing it this way where 1 meter equals 10 decimeters, totally fine. They're both exactly correct, right? So in this case, we would say that 0.1 meters per 1 decimeter is our first conversion factor. And then there's 1 decimeter per 0.1 meters is our second conversion factor. Jewelry that contains 18% gold. Well, that means that the jewelry, for every 100 grams of jewelry that we have 18 grams of gold. So 18 grams of gold equals 100 grams of jewelry. Or we would say 18 grams of jewelry, 18 grams of gold per 100 grams of jewelry, or 100 grams of jewelry per 18 grams of gold, depending on what we want to use there. Finally, 1 gallon of gas is whatever number it happens to be. Well, so this is a conversion from gallon, which is a volume unit, abbreviated as GAL, and to dollars, which is, of course, a money unit. In this case, it's $2.4 for every 1 gallon, or 1 gallon for every $2.4. And I know we switched to 5.4, but hopefully you get the idea from all of that. Okay, now here's the whole point. This is why we're using conversion factors, because they're a very convenient way to solve problems. And problems that we encounter, not just in chemistry, of course, it's going to happen a lot this semester in chemistry. We're going to use a lot of conversion factors, but it's also going to come up a lot in everyday life. Like these are conversions that you do in your head, right? So like if you go to the gas station, right, using the last problem, you know that you only have $10 and you need to figure out how much gas can you buy for that $10 and how far can that get you? Well, you're doing a lot of math in your head because you're going to figure out how many gallons of gas can you afford given an amount of money. So it might be, so let's say that we have $10. And this isn't exact, right? This is you have a $10 bill, let's say. And you know that gas is going to cost, let's go $4.59 per gallon. Well, in order to solve this problem, you need to use a conversion factor. And again, this is something that you would do in your head. What we're going to do is we're going to formalize it and show you how it's formal in how to use it in a formal setting. And hopefully this will kind of clarify your everyday uses of this type of problem, and then also kind of apply it to chemistry and in the future to medicine probably. Okay, but I'm getting a little bit ahead of myself. Here's what we're going to do this type of problem solving. The first thing that we want to do is we want to identify what unit we're given, and then also identify what unit we need to get to. So the way I always do this is I start with just what I call a solution map. Oops, hold on. So I'll start with given, identify what that is, and I know I need to get to the needed unit. So now in this case, we need the gallon amount, and we're given the dollar amount because we know we only have $10 to spend. Okay, step 2, write a plan that converts the given unit to the needed unit. Well, okay, so we have dollars. Can we convert from dollars directly to gallons? Sure enough, we can. We have $4.59 per gallon. So we can convert from dollars to gallons. Now that's a little boring. So what if we instead say, rather than worrying about this, let's say that we want to figure out the number of miles that we need to travel, or the number of miles that we can travel on a given amount of gasoline. Now, we can't go directly from dollars to miles, but if we know how to get from dollars in our pocket, our $10 bill, to the gallons of gas using the price of gas, then we can get from gallons of gas to miles traveled by using the fuel economy of our car, or the miles per gallon. So then we can make sure that we can get to campus or wherever we need to go. So this is an idea of like a solution map or a plan that's going to get us from our starting unit to our needed unit. Then identify one or more conversion factors that are going to cancel out the units and get you to that needed unit. That's what we've done here with the price of gas in miles per gallon. And then finally, set up the calculation and then execute the calculation. Okay, let's give an example first, and hopefully this will start to make a little bit of sense here. Okay, example. If a person weighs 178 pounds, what is their body mass in kilograms? Okay, so first up, that's a little too much right there. Let's go ahead and follow our solution map pipeline. First off, what are we given in terms of units? Our given unit is the pound, right? So we know that we have 178 pounds for this person's weight. And we want to get it, so this is given. And we want to change that to the needed unit, which is the kilogram. That's what we're asked for. Okay, so given to needed. Now, is there a way to convert directly from pounds to kilograms? Sure enough, there is. There's a direct conversion from pounds to kilograms. It's that 1 kilogram equals 2.20 pounds. Okay. So that's going to be our plan. We're starting from pounds, we're going to kilograms. And this is another way that you can set that up. Whichever way you prefer, totally fine by me. You're given 178 pounds, you need the answer in terms of kilograms, and you know that you have a conversion factor to get from pounds to kilograms, a US metric factor. Okay, so step 3, you're going to go ahead and get the equalities and state the conversion factors. In the future, of course, once you know the equalities, you'll be able to get the conversion factors right away. If you have 178 pounds and you need to convert it into a kilogram amount, which conversion factor is going to be useful to you? Is it the pounds per kilogram or the kilogram per pound? In this case, what you need to do is use the per pound measurement. So 1 kilogram per 2.20 pounds. And the reason for that is you'll recognize I'm going to have this pound in the numerator divided by this pound in the denominator. In other words, these units are going to cancel out. And then I'll be able to execute my plan from here. 1.78 divided by 2.20, that'll give me my answer in terms of kilograms. Now, what would happen if you had, did it a different way? What if you used 2.20 pounds per 1 kilogram? Well, now note you have a pound times a pound in the numerator divided by a kilogram. So none of these units cancel out. And rather than getting the clean kilograms, you would have pounds squared per kilogram, which is just an insane unit that no one would ever use, right? So that is definitely not going to be the way to do it. I hope that makes sense. So down here is our calculation. We have 178 pounds times 1 kilogram divided by 2.20 pounds equals, just plug it into your calculator. When you get it into your calculator, you end up with, oh, I lost my calculator here. You get a number. So I'm going to make up the number here real quick. Say it's 80.872 in your calculator. Now you need to know, where do I round it? This is where we apply our significant figure rules from the previous lecture. 178 pounds, how many significant figures? 1, 7, and 8, so 3 significant figures. 2.20, 2 and 2, and then obviously and then the 0 is a trailing 0 in a number that contains a decimal, so that is significant, so 3 significant figures. So a 3 significant figure number divided by a 3 significant number means we need 3 significant figures for our answer. We go 1, 2, and 3. Look to the right, it's a 7. We round up. That gives us our answer here, 80.9 kilograms. Again, I don't know if this was the exact answer. I got to find my calculator somewhere. But this hopefully gives you an idea of how you would solve that in that case. Okay, here we go, guys. Give it a shot. A rattlesnake is 2.44 meters long. How many centimeters long is the rattlesnake? Again, this is another example where you were able to measure the snake once. You don't want to measure it again. So convert from your first measurement to another measure. This is 2.44 meters long. Convert that into centimeters. This is sample exercise number 18. Go ahead, give it a shot. If you have any questions here, we're going to answer it in just a moment. But pause the video and please give it a shot. Okay, so we're back. Now, how do we do this? Well, we're given the length in terms of meters, right? So we know it's 2.44 meters. And we need to get it into centimeters. So how can we convert from meters to centimeters? Well, is there an equivalence that gives us the conversion factor from meters to centimeters? Sure enough, we know that 1 meter is equal to 100 centimeters. So what we need to do is find the conversion factor that cancels out meters and gives us centimeters. So that would be 100 centimeters per 1 meter. Meters cancels out. That gives us 2.44 times 100, or 244 centimeters. So it's just that easy in this case. Again, you could recognize it this way as well. If you're given 2.44 meters and you need it in terms of centimeters, you know that your conversion factor has to be centimeters per meter. Well, fortunately, meters and centimeters are both related in the metric scale. So you know that there's 100 centimeters per 1 meter. Use that as your conversion factor. Now, the length of the rattlesnake was measured, 2.44 meters. There's 1, 2, 3 significant figures. 100 centimeters per meter, that's a defined number. So that's an exact conversion. So you don't have to worry about the significant figures for this. So sure enough, the measurement was 3 significant figures. That means our answer should be 3 significant figures at 244 centimeters. Okay, so that's all fun, converting these relatively simple problems one to the next. But as you can imagine, it gets more complicated, right? I already showed you a more complicated example where we were converting from money to gallons of gas to miles that we could travel in our car. So same thing here with, now what we're going to do is we're going to use 2 or more conversion factors. And this is, again, something that we're going to do throughout the class. So most of the time when we have these types of problems, it's not simple enough that we're going to have a conversion factor from one to the other. Oftentimes we'll need an intermediate unit or multiple intermediate units to get from what's given to what's needed. So the way that we're going to set this up is basically we have our given unit, we use a conversion factor to get to the first intermediate unit, then we use our conversion factor to get to the needed unit. So 2 separate conversion factors have to be used. Let's go ahead and give you an example. Okay, so sorry, this is a lot on the screen right now, but let's just look at the example first. A doctor's order prescribed a dosage of 0.150 milligrams of Synthroid. If you only have 50 microgram tablets in stock, how many tablets are required to provide the prescribed dosage? So what you're given is, you know that you have 0.150 milligrams of Synthroid. That's going to be what you need to administer to the patient. Now the thing is, you're not going to like measure out Synthroid into a little weigh boat and then give that to the patient. No, you have these 50 microgram tablets, and you need to figure out how many tablets am I supposed to give to this patient. Okay, so what's our plan, right? So we're starting from milligrams of Synthroid. And we're trying to get to tablets of Synthroid. But the problem is we don't know the terms, the number of milligrams of Synthroid that are in the tablets. We only know the micrograms of Synthroid. So this could be our connector, right? If we can get from milligrams of Synthroid to micrograms of Synthroid, now all of a sudden, now we have our conversion factor here where we have 1 tablet equals 50 micrograms. And that can be our conversion factor there. So if we can get from milligrams to micrograms, can we do that? Sure enough, we can, because they're two metric units. So we can use the metric conversion factors here. Okay, so first up, we can find that 1 milligram equals 1,000 micrograms. Now we've done this a lot already in this chapter. As you can imagine, like the things that I'm going to repeat to you over and over again are things that may come up in practice, basically medical practice. And so that's kind of what we like to focus on. The conversion from milligrams to micrograms is going to be very important. I'll show you this one more time, but remember the way that we figured this out was that we know that there's 1,000 milligrams in every 1 gram. We know that there's 1 million micrograms in 1 gram. If you set these 2 together, you would get that 1,000 milligrams equals 1 million micrograms. If you divide both sides by 1,000, then finally you end up with this equality here, that 1 milligram equals 1,000 micrograms. And again, I'll just repeat it one more time. That's extremely important for your future. So just keep that conversion factor in mind. And so, because it's going to show up again and again on the test. As I mentioned, I'm not going to give it to you on the test. It's one of those things that we just want to bake into your brain as much as we can in this chemistry class. So the conversion factor would be 1,000 micrograms per 1 milligram, or 1 milligram per 1,000 micrograms. Likewise, we have 50 microgram tablets in stock. That means that 1 tablet equals 50 micrograms of Synthroid. So our 2 conversion factors here would be 50 micrograms of Synthroid per 1 tablet, or 1 tablet per 50 micrograms of Synthroid. Okay, well now we have to set up our conversion factors. If we're starting from 0.150 milligrams of Synthroid, well then our first one, we know that we have to cancel out the milligrams. So the milligrams has to be in the denominator, 1 milligram synthroid. And then micrograms is going to be on top. That's 1,000 micrograms of synthroid. Okay, so milligrams cancel out. Now we're ready. We can convert from micrograms to tablets. So tablets is the unit that we want. So that needs to be in the numerator. The one that we want to cancel out is micrograms. So we're going to put that in the denominator, 50 micrograms. Okay, and then we're ready to do our calculation. Now 0.150, that's a 3 significant figure number, right? The 1, the 5, and the 0, trailing 0, and a number with a decimal. The conversion from micrograms to milligrams, or vice versa, is an exact number. It's a metric conversion. So don't worry about the significant figures there. Now 1 tablet is counted, but 50 micrograms here is measured. So 50 with the decimal point micrograms, that means we have 1 and then the 0, trailing 0, and a number with a decimal, also significant. So that's 2 significant figures for that one. Now in the end, that doesn't apply because we end up just having an answer of 3 tablets. Sure enough, you could say 3.0 tablets if you wished, but 3 tablets is also acceptable since you're just going to count out the 3 tablets. Okay, here we go. Give it a shot with what you already know about conversion factors. Tell me how many minutes are in 1.6 days. Use the conversion factor sample that we showed you to go ahead and give us an answer here in sample exercise number 19. So go ahead, pause the video. When you come back, we'll have the answer. Pause. Okay, we're back. Now, what do we know? Well, we're given 1.6 days. And we need to convert to minutes. Now, the thing is, I don't know how many minutes are in a day. Maybe you do, but I don't know that conversion factor. However, I do know how many minutes are in an hour, and I know how many hours are in a day, so I can use that as an intermediate conversion factor. The 2 equalities that we're going to have is that 1 day equals 24 hours, and then 1 hour equals 60 minutes. So the conversion factors would be 24 hours per day, and then 60 minutes per 1 hour. Our 1.6 days is going to be converted to hours first, 24 hours per 1 day, and then an exact conversion of 60 minutes per 1 hour. That gives us our final answer of 2,300 minutes. Now keep in mind here, we have 1.6 days. 1.6 days, that's 2 significant figures. That means our answer also needs to have 2 significant figures. So keep that in mind. Okay, here we go. Sample exercise number 20. If your pace on a treadmill is 65 meters per minute, how many minutes will it take you to walk a distance of 7.5 kilometers? So let's go ahead. I'm going to grab my calculator here. So I'm going to pause the video. You pause the video too. Give it a thought. Now, keep in mind, what are you given and what are you asked for here? So it's a little tricky here. It's a little different than what we saw before. So go ahead, give it a shot. I'm going to get my calculator. When I come back, I'm going to go over the answer. So what are you given here, right? You're given that your pace is 65 meters per minute. Is that a starting number? Is that what you're given really? Or what that actually is, it's a pace. In other words, it is a conversion factor. We know that there's 65 meters traveled for every 1 minute on the treadmill. So that's going to be actually our conversion factor in the end. What we're given here is 7.5 kilometers. So we're starting from 7.5 kilometers. And what are we supposed to get? It says how many minutes does it take? So we need to turn this into minutes. Well, we don't know our pace in terms of kilometers per minute, but we do know it in terms of meters per minute. So if we're able to convert from kilometers to meters, and then from meters to minutes, no problem. Well, kilometers to meters, that's no problem, right? That's a metric. Meters to minutes, that's given on our pace right here. So we can just use that as our conversion factor. So let's go ahead and take a look. Oh, so this I showed you. Our 2 conversion factors here are going to be 1,000 meters per 1 kilometer, and then 1 minute per 65 meters. Set it up like this: 7.5 kilometers times 1,000 meters per 1 kilometer. Kilometers cancel out. Then 1 minute per 65 meters. That's our pace that we measured before. Meters cancels out. And that gives us our answer here, 120 minutes. Note here, we have an exact conversion, that's the metric conversion. 65 meters per minute is measured. So there's 2 significant figures in the 65 meters, and then 2 significant figures here in the 7.5 kilometers. Okay, all right. So last little bit of the chapter, we're going to talk about density very briefly, which is again something that you know about a lot. You use it every day without even thinking about it. But again, we're just going to give some formal background to it so that you're kind of more familiar with it in terms of chemistry. So density is the relationship between the mass of an object and its volume. So what you do is you take the mass of a substance and divide it by its volume. That's this density equals the mass of a substance divided by its volume. This is often given, and you'll see this on the test as D equals M over V. Now, so again, that's very formal and dry definition of it, but density is something that you kind of understand because it basically tells you like how much stuff there is in a substance. So okay, so here's the obvious. Like take your water bottle. Now, when you have a water bottle that's full versus a water bottle that's empty, what is different between the two of them? The volume is the same, right? The water bottle is going to be the same volume, whether it's full of water or it's full of air. Okay, but you notice the difference a lot when you're carrying a full water bottle versus when you're carrying an empty water bottle. Now, why is that? Well, the difference is the stuff that's inside. If you have water inside, water is dense. It's about 1,000 times more dense than air. So there's a lot more mass in your full water bottle compared to the empty water bottle that just contains air. Air is much less dense. And so the empty water bottle ends up being much lighter than the full water bottle. That's why, like, if you're in a fight, you use a full water bottle, that's going to really do some damage, whereas an empty water bottle might not do so much. Okay, so we're going to talk a lot about density when we talk about solids, liquids, and gases in the future. But keep this in mind that higher densities usually arise when particles are closely packed together. Basically, again, it's the idea of density is like how much stuff is fit into a unit of volume. And the more closely the particles are packed together, the more particles fit. Those particles are what actually have mass. So you have more particles, you have more mass. And then in general, lower densities are contain particles that are farther apart. So you end up with gold and lead being very high density materials, not only because their atoms are packed closely together in solid form, but also because their atoms contain a lot of stuff. They contain a lot of subatomic particles. And we're going to talk about that in the future. But the idea is, you know, an atom of gold contains many more protons and neutrons than does an atom of, say, carbon. So that's why diamond is relatively light, whereas a gold is relatively dense. Okay, so the units that we're going to use for density are usually going to be expressed in terms of grams per milliliter, but also sometimes in grams per cubic centimeter. Now, fortunately, those are equivalent, right? Remember, we talked earlier that 1 centimeter cubed equals 1 milliliter. So if you have a unit of grams per centimeter cubed or grams per milliliter, that's the same. You're comparing apples to apples. It's the exact same amount. Now, gases, I already mentioned that air is about 1,000 times less dense than water. So because gases are so, they have such low density, we use a different unit for their density. We describe it in terms of grams per liter. So the grams per liter, of course, describes the amount of mass in a much greater volume than does the gram per milliliter. Okay, so here's your density table of some common substances. You don't need to memorize any of these, but it just gives you kind of an idea here. Some kind of interesting things, like for example, water. So here's the classic one, is that water at 4 degrees Celsius has a density of 1.00 grams per milliliter. That's great, right? I mean, another reason to use the metric system is that this conversion factor for the density of water, so useful. You can get from grams to milliliters of water, no problem. Now, olive oil has a density of about 0.92 grams per milliliter. So think of like when you make a vinaigrette, you have balsamic vinegar and olive oil. You know that the olive oil is going to float on top of the balsamic vinegar, and that's because it's less dense. So things that are less dense float, things that are more dense sink. And that's kind of the whole point of this discussion of density. What did I want to say here? Anything else? Note as well that solids tend to be more dense than liquids. So like gold, lead, silver, copper, iron, salt, bone, sugar, muscle. Excuse me. These are all things that are more dense than water. The exception, of course, being two very important ones. Oils tend to be less dense, so things like olive oil, body fat. And then very importantly, ice is less dense than water. And that's for a reason that we'll talk about in the future. So solid water is actually less dense than liquid water. Water is like the only substance that has that property. And turns out it's extremely important. And if that weren't the case, there'd be no life on Earth. We'll talk about that later. Okay, so how does this relate to health? Well, you may have heard of the condition called osteoporosis, which is just a thinning of bones. You can take basically images of the bones, and you can see that a lot of the bone material, the calcium bone material, is actually eaten away when you have osteoporosis. So you have much less dense bones, and those less dense bones then can then lead to easier fractures, basically, in your bones. You can actually determine bone density using X-rays, and in particular, they do it at the narrow part of the top of the femur and the spine. And bones that have high density there will block more X-rays compared to bones that are less dense. So that's how you can see the onset of osteoporosis. Okay. Now, this is something that we're going to do in lab, so I'm not going to spend a lot of time on this, but one way that you can measure density is by using what's called volume displacement. So basically, if you take a solid and completely submerge it in water, it displaces its own volume of water. Now, this makes sense, right? If you've ever taken a bath, when you get into the bath, like you're going to displace, the water level rises, right? That's because the volume of you is displacing the volume of water up the bath. And if you get enough people in the bathtub, it's going to overflow, right? Or the hot tub, whatever it happens to be. So the idea is you can get the mass of a solid very easily using a balance like what we have in lab. You can get the volume of a solid, well, if it's a regular object, so if it's like a geometric solid, no problem, you can measure the length and height and stuff, but that's not always the case. Sometimes you have irregular solids and you can't get the measurement that easily. Well, you can stick it in water, the volume of water initial, subtract that from the final volume of water. In this case, it ends up being 9.5 milliliters. That gives you the volume of the submerged object. So in this case, the density of the zinc is going to be the mass of the zinc, 68.60 grams, divided by the volume that it displaced, 9.5 milliliters. And that gives us our answer here in density in grams per milliliter, 7.2 grams per milliliter. Okay, here we go. Sample exercise number 20. What is the density in grams per milliliter of a 48.0 gram sample of a metal if the level of water in a graduated cylinder rises from 25.0 milliliters to 33.0 milliliters after the metal is added and fully submerged? Okay, given what you know about density, go ahead, give it a shot. When you come back, pause the video now. When we come back, we'll have the answer and we'll discuss density. Okay, we're back. So what happened? Well, the volume of the displaced object is just going to be the final volume of the water plus the metal minus the volume of the water initial. So that's 33.0 milliliters minus 25.0 milliliters. That's 8.0 milliliters. The density is the mass of the sample. That's given to us right there, 48.0 grams divided by 8.0 milliliters, ends up being 6.0 grams per milliliter. Now, another way you can take this further is I might ask you on a test, for example, what metal might this one be? Well, what's cool about density is it's a definite property for a given metal. Like, for example, silver is always going to have a mass of 10.5 grams per milliliter, or I'm sorry, a density of 10.5 grams per milliliter. So if you measure a metal and it looks like silver, but its density is not 10.5 grams per milliliter, that tells you that your metal is not actually silver. So this is the famous Archimedes principle. That's a famous way of like figuring out what the density of something is. So like what you could do in the test problem, you determine the density, then you look at this table and say, 6.0 doesn't really match any of these. So I can't figure out what it is, Professor Daub. And then I'd have to like go back and say, oh, maybe it's 9.0. Which one's closest to 9.0? That's copper. So you choose copper. Okay, all right. Now, another thing that you can do with density is that you can use it as a conversion factor. If the volume and the density of a sample are known, then you can calculate the mass in the grams using the density. Okay, so here we go. Here's our example problem. An unknown liquid has a density of 1.32 grams per milliliter. What is the volume in milliliters of a 14.7 gram sample of the liquid? Well, if we're given 14.7 grams, we need to convert it to milliliters. How can we convert it? Well, density in this case is going to come to the rescue. Basically, if we have a density of 1.32 grams per milliliter, that means that 1.32 grams of the substance equals 1 milliliter of the substance. So that gives us our equality. And then from our equality, we can determine our conversion factors. 1.32 grams per 1 milliliter and 1 milliliter per 1.32 grams. Then all we have to do is set up the problem. 14.7 grams times, well, we need milliliters, so that's going to be in the numerator. Grams is going to cancel out, so that's in the denominator. So times 1 milliliter divided by 1.32 grams. And we end up with, to three significant figures, 11.1 milliliters of liquid. Okay, so here we go. Let's go ahead and give it a shot. Sample exercise number 22. John took 2.0 teaspoons of cough syrup for a cough. If the syrup has a density of 1.20 grams per milliliter, and there's 5.0 milliliters in 1 teaspoon, what was the mass in grams of the cough syrup? So we're given the teaspoons. We're given the density in terms of grams per milliliter. So we need to convert from teaspoons to grams. All right, now using the density, go ahead, give it a shot with sample exercise number 22. Once again, I'm going to ask you to pause the video. When you come back, we'll take a look through the answer. So go ahead, pause. Okay, so let's go ahead and take a look here. We know that we're starting from 2.0 teaspoons. And we need to convert this to grams. Now, we don't know how to get directly from teaspoons to grams because we're not given that density. However, we are given the density in terms of grams per milliliter. So if we can convert from teaspoons to milliliters, which sure enough we can, using a US metric conversion, and then we can get from milliliters to grams using the density. So that's how we're going to figure this one out. Okay, so I already mentioned that. So our two conversion factors here are 1 teaspoon equals 5.0 milliliters, and 1 milliliter of syrup equals 1.20 grams of syrup. That's the density. So starting from 2.0 teaspoons, we know that there's 5.0 milliliters per 1 teaspoon. We set up the teaspoon to cancel out here. 5.0 milliliters in the numerator, and then 1.20 grams per 1 milliliter. Milliliters again in the denominator, now to cancel out the milliliters from before. That gives us our answer to two significant figures of 12 grams of syrup. Okay, last part of this chapter, very brief mention, but this is something that does come up in medical terms a lot, which is specific gravity. Now, the specific gravity is a very closely related concept to density. And what it is it's the relationship of the density of a substance and the density of water. What you do is you take the density of a sample and you divide it by the density of water, which is 1.00 grams per milliliter. So your specific gravity, or SPGR, ends up just being the density of the sample, just without the unit, basically. So you take your density of the sample divided by the density of water. Now, what this actually is why this is important, is because this is how we compare. Basically, we can figure out the density of urine using this hydrometer. Basically, the density of urine can tell you a lot about a patient's health. Basically, the normal range is going to be from 1.003 to 1.030. If it's lower than that, that means that can indicate that the patient has type 2 diabetes or some type of kidney disease. And if you have an increased specific gravity, that can occur due to dehydration, kidney infection, or liver disease. So again, this is just a measurement, just kind of showing you how specific gravity is related to density, and then kind of understanding how we use that in health methods. Yeah, okay, and yeah, so there's also these other ways that can figure out the specific gravity of your urine here, not using the hydrometer, which is this here. But again, just kind of showing you the use of these terms. Now, I believe that finishes up chapter 2. So go ahead, finish up those sample exercise packets. I'm going to see you guys in lab here very soon. And now that we're done with chapter 2, ready to move on to chapter 3 with lecture 4. Let me know in the comments below if you have any questions whatsoever or any comments. And I will get back to you just as soon as I can. So, all right, I'll see you guys very soon. Bye-bye.